Hey everyone, I hope you're doing well. Welcome back to another video. Today we are on part 4 of the Transformer from Scratch series. If you're joining this series for the first time, welcome. The mission of this series is to explore, comprehend, and ultimately cultivate a deep and intuitive understanding of the Transformer architecture. Let's jump right into today's lesson. So let's first start by reviewing what we talked about in part 3 of this series, which is the last video. So we talked about second order sequence models with skips. Basically, for predicting the next word after ran, we can refer to any word that occurred before the word ran, right? And we saw that we can express this prediction as a form of voting system and essentially features, right? So if we want to get the probability or, well, essentially vote of the next word being down, we simply add up all the weights here or features, right? And we will see that one of these has a higher weight, so then we choose one of them over the other for the next word, right? So these are the two sentences we have, and we can build two words like this, right? So ran, it can refer to any word before that, right? Okay, so that was just a quick review. Now, we're going to be learning something new today called masking. So consider the case where the difference between the votes is really small, like 0.5. In our example here, the difference, if you calculate it, is actually 1, which is still relatively small, right? Imagine if we have 100,000 different commands or different sentences like this, right? Then our model will be even less confident, right? Because we have such diverse possibilities here. So what can we do, right? We can essentially make the prediction better by ignoring the uninformative votes, right? So for the votes here, this 0.5 really doesn't do anything, right? Because we have 0.5 going to down and 0.5 going to please, right? It doesn't actually make a huge difference. But the votes that do matter is battery and ran going to down, right? This has a vote of 1, which is very significant. So we can consider battery and ran, this word combination, to be significant. Another one will be program and ran, right? Because these two are distinct words. Others are just repeating themselves, right? And again, we're trying to predict the word after ran. So that's why you don't see please and down in these combinations. Okay, so we only really care about battery ran and program ran because the other combinations are in both commands. So now, how can we remove these useless features, right? We don't really need them because they don't provide us with any actual useful information for predicting the next word. Well, this is where we apply the idea of masking. A mask is simply a vector filled with ones and zero. Okay, so this is a mask, right? So essentially it's filled with ones and zeros. And the ones are the combinations or features that are important, while the zeros are the features or combinations that are unimportant, right? So in our case here, the important ones are battery and ran, right? These two combinations are important. And let's say this vector is one hot vector represents this sentence, right? Check the battery log and find out whether it ran down, please. Right, so that's the sentence we have before the before and including the word ran. Right, so that's why we see one here, one here. Actually, sorry, no, we include the entire sentence. So we have 0 here because we haven't reached there yet. And we have 0 here, 0 here, 0 here, right? Because program ran, for example, doesn't exist in this sentence, right? So that's why 0. And we simply multiply it element-wise by this mask, and we result in this vector that has no noise, right? We simply remove all these useless features. Now we are left with something that's pretty clear and simple, right? Essentially, we made the important features stand out. And we see in this case, even though this is 1, it's still ultimately 0 because we don't have the word program and ran in there. Okay. And this process of selective masking is actually called attention. And this is actually really important in the transformer architecture. So a little fun fact for you, the original paper that introduced the transformer architecture is called Attention is All You Need, right? So just to stress how important the idea of attention is. And this paper has over 81,000 citations. That's very large number, right? Typically, even if you have 100 citations, that's considered quite a lot. And 81,000, that's a very large number, just to stress how important this paper is and how groundbreaking this invention is, right? Okay, so now we are more confident in our predictions for the next word after we removed all the noises or unimportant features, right? So essentially, we went from this down to this. Now, this is very clear, right? Okay. Now, we're actually going to be digging into the transformer model now. So the selective second order with skips model, what we just talked about, is very useful to think about what the transformer actually does. It actually mirrors what many modern large language models do too. So now let's talk about what inspired the transformer architecture in terms of practicality, right? Why is it designed the way it is? Well, the first thing we have to consider is that computers are great at matrix multiplications, right? So NVIDIA is focused on building hardware that is optimized for matrix multiplication. Basically, it means that any computation that can be expressed in the form of a matrix multiplication can be extremely fast. So whenever possible, we want to express things as matrix multiplications. Second, each step needs to be differentiable for backpropagation. Remember that weight updation with optimization algorithms like gradient descent require differentiability, right? So that means given a change in a weight, we must be able to calculate the loss, right? So I have a cool graph here from one of my older videos. And as you can see, with some changes in the weight, we have to be able to calculate the change in loss, right? So it has to be differentiable here. And third, the gradient needs to be smooth. This means that the slope can't go up and down, right? Given a small change in parameter weight. So this is pretty smooth, right? We can easily estimate where the minimum is here, right? Okay, so after we talked about that, now we can move on to attention as matrix multiplication. So how do we actually obtain the attention mask vector? How does transformer find the relevant mask, right? So remember how we just talked about how computers are great at matrix multiplication? Well, we should probably do something with that, right? So just to give you an example of how we could do that, we could stack the mask vectors for every word into a matrix and use one hot feature vector to extract a specific mask vector for a word, right? So let's say we have this sentence, we have a lovely dog. Then we are trying to get the mask for the word have, right? So we have one here, this is one hot encoded vector. We have a one here, and essentially by multiplying this, we obtain this specific row here. And, each column represents some word pair. For example, we have a, right? Whatever, right? And, or essentially just a single word because they all have the same, right? So essentially here we obtain this specific mask vector through the multiplication of a one hot feature vector and this stack of mask, right? We call this one hot feature vector the query vector, and the stack of mask vectors the keys, right? This is denoted by K transpose. K is a matrix here. And I'll explain why we take the transpose. But if you don't remember what the transpose is, essentially we flip it, right, across the diagonal of a matrix. So this element here after transpose will be here, and this element here after transpose will be here, right? Okay. And this actually represents a very important part of the transformer. This mask lookup is inside the attention equation here. See? So this query vector multiplied by the transpose of the K vector, or the keys. And we take the transpose of the keys matrix because it's stored in columns initially, not rows. So after we take the transpose, it's actually stored in rows here. Okay, so yeah, that's why we take the transpose before multiplying it, so we can actually extract the relevant mask vector. Okay. Now let's talk about second order sequence model as matrix multiplications. So how can we construct word pair features, right? How can we construct them with multiplication? Because we just talked about how important matrix multiplication is in deep learning. We can actually, before that, so what do I mean by word pair features? So how do we construct something like this, right? Where we have this specific feature pointing down, right? So how can we build that? That's what I meant. Okay, so we can actually use a single layer fully connected neural network here. So to keep it simple, we have the word battery, program, and ran. We extracted these after applying the mask vectors. So these are the three words that we really care about here. They're the important words. And we have here a single layer fully connected neural network, right? And essentially, if we combine them in a specific way, we actually get a feature representation. And just to keep in mind, this is extremely simple and does not bear any resemblance to what the weights would actually look like in training. So this is just to help you visualize and understand how it works. And theoretically, right, when combining these, we could result in three word combinations, not just two. Okay, so we can also represent that as a matrix here, right, where each row is the specific weight for a word in the construction of this feature, right, this word pair feature. Now, let's say we're focusing on this sentence. Check the battery log and find out whether it ran down, please. We can multiply, right? We have these important words here, and we have a bias term. So we have a bias term in here for a fully connected neural network because it gives you more freedom, right? Okay. Now, and this bias term can be trained in actual training, so can all of these weights. Okay, so we have these words here, and since we're focusing on this sentence, we don't have the word program, so that is set to 0. And we multiply by this matrix we just came up with, right? Essentially the weight matrix to represent these word pair features. So after we multiply them, right, we end up with 1 and -1. So these are the word pair features for these two words. Essentially the same thing as up here, right? Okay. And now the final step is to apply the ReLU activation function to introduce nonlinearity, right? So the ReLU activation function is very simple. It essentially replaces any negative numbers with 0, right? So the function, let me try to graph it real quick. The function looks something like this, right? Where that's a line, right? So any negative number we have, it's mapped to 0 here. Okay. And this essentially cleans up the feature so that we can have 1 represent the presence, or anything greater than 1 represent the presence, and 0 represent the absence, right? So we don't have program here. And we don't have program run this specific word pair feature here. And putting everything together, we have this formula for the fully connected neural network. So first, we take the max of 0 and the multi-word feature creation matrix times the masked word activities, because this code essentially represents the ReLU activation function. And this is the masked word activities, which is essentially all the words that we care about after applying mask. And we multiply it by the matrix here, right? So this is essentially the step up here, right? So essentially we're doing the same thing as here. Okay, and we take the max between 0 and whatever we have here. And finally, we multiply by the selective second order transition matrix. Okay, and yeah, that's it. It's pretty simple. And I know this is probably a lot to take in. It will make sense eventually after we put everything we have learned together. And yeah, feel free to review the video. So what we have talked about here is essentially the feed-forward part of the transformer architecture. Okay, so just for a quick review. Yeah, I could have just scrolled. So first we talked about masking, which is essentially cutting out all the noises and only focusing on the words that we care about, or features that we care about, right? So we only care about these two features, word pair features. And this process of selective masking is called attention, which will prove to be very important to the transformer architecture. And we talked about what inspired the transformer architecture in terms of practicality. So, we have to focus on matrix multiplications. Each step needs to be differentiable and the gradient needs to be smooth. Okay. And we also talked about how we can express attention as matrix multiplication, right? Because we want to have as many things expressible as matrix multiplication as possible. And essentially here we stack the mask vectors so that we can extract them easily through one hot feature vector lookup table, sort of. And we talked about how that actually represents matrix Q, or query times the key matrix to the transpose, right? The transpose of the keys matrix. And finally, we talked about second order sequence model as matrix multiplication, right? How do we actually construct these word pairs, right? Given these words, how can we end up here? And this could theoretically end up with 3 words, right? Okay. And yeah, that's pretty much it for today's video. If you have any questions or anything that you're still confused on, please ask in the comments below, because I know this is probably a lot to take in. And things will become clear as we progress through the rest of the series. So, and also I'll try to upload more frequently. Sorry for my terrible upload schedule. I was on vacation for the past few weeks, so I wasn't really able to get my recording done. And yeah, thank you guys for watching, and see you next time.